Welcome to the Manganate 7 Redox titrations video. Okay, 23.2 in chapter 23. Okay, so let's start sharing the screen. Okay, so hopefully we don't want to stop the video yet, but let's move that down a bit. Okay, so just a few bits of housekeeping. Obviously, trying to keep up with past paper questions, doing your workshops. Well, coming along to workshops if you need them. If you're finding you're going on fine, that's good. You don't have to turn up, but it's really good if you come along with some questions that you're stuck on, some of the harder questions perhaps. Okay. So what we did last time, if I go back a bit, yeah, there we go, is the half equations for the acidic and the alkaline fuel cell. And I mentioned the fact that it is a potential way of reducing our use of fossil fuels. So the hydrogen fuel cell, so we have got two half equations for that. Hydrogen plus oxygen making water is going to give us electricity. So we work it out like this. So we've got the acidic part with the hydrogen making H+, and we've got the alkaline part with the hydroxide. And yeah, there we go. So you can either solve it with acidic in the acidic way by adding H+, or you can do it in the alkaline way by adding OH-. So here with the 2H2, okay, we know we're going to make 4H plus because we've got the hydrogens here and we get 4 electrons. To balance up the O2, to get it to water, we need to add electrons to oxygen because it's already 0. We need to make it -2 in the water molecules. So if we've got O2, we're going to get 2 water molecules. We're going to need to have 4 electrons, okay, because we've got 2 oxygens. We need to get both of them to -2, so we need to add 4 electrons. And then we've got hydrogen here to make the water to balance the oxygen up, and therefore we need to have 4 hydrogens, H+. So this is the acidic way of doing the alkaline to doing the hydrogen fuel cell, and this is the alkaline way. So we've got 2H2 here. Okay, again we're going to make we'll make 4 waters this time. We'll get rid of 4 electrons because we're still going to get rid of the 4 electrons to make the hydrogen become from 0 to -1. Okay, 4 electrons are doing that. So therefore we need to add 4 hydroxides because we only had 4 electrons here. We're going to need to have 4 over there. Okay, so it's all balanced up. So if you need to stop the video and have a look at that. Okay, so we're just building very easily on from the Manganate-VII redox reactions that we did before. So we'll be going through these points, okay? And what we'll need to do is we're going to look at how we do the titration calculations, and that's the sort of newer stuff, okay? So here's a nice link to a news story, okay? This Canadian town, the municipal people who are in charge became very sorry because they had pink tap water. Okay, so if I bring that story across, okay, I'll probably need to make that a bit smaller. Yeah, it's a bit big there. Okay, so basically this Canadian town apologized after the water treatment plant turned the water supply pink. Okay, there's no public risk, but I mean, obviously there's various things going on, like they didn't tell everybody it was going to happen. It's a side effect. Common water treatment, potassium permanganate is used to remove iron, okay, which you'll see when we do the look at the equation in a bit, and hydrogen sulfide from water, okay. So a valve malfunctioned and let too much of the potassium manganate in and just basically colored all the water pink. Okay, right. Okay, so let's move forward then. So, this is why they use the potassium manganate, because it's a very good oxidizing agent to oxidize the iron and then therefore get rid of it. Okay, so in acid solutions, it's reduced to Mn2+. It's not balanced. We balanced this last time. Okay, so just a recap of this. So we need to balance the non-hydrogen oxygen elements. So the manganese is balanced. I've got 1 manganese on the left and I've got 1 manganese on the right. So that's okay. Next step is to balance the oxygen. Well, this is a different, we actually balance it with the water next. So here we're showing slightly alternative way of doing it. So we've got 4 oxygens on the left-hand side, so we're going to need to have 4 waters on the right hand side, which will therefore contain the oxygens. And so now we could balance the hydrogen now. So we haven't used the oxidation numbers in this method, okay, so far. So what I'm doing is I've got 4 H2s here, so I'm therefore going to need to have 8 H plus, okay. So just bear in mind this is a slightly different way of balancing this equation. So I've now got my 8 H plus, I've got a minus on that side as well, so I've got +7 and I've got +2 on the left hand side. So now I can balance the charge with electrons, so I need to add 5 electrons here, okay, onto the left hand side. So can you see we haven't used oxidation numbers to balance it this time, we've actually just done it by balancing up the electrons. Well, first we balanced our manganese. It was already balanced, that was fine. Then we balanced the oxygen. We got we got O4, so we need 4 waters, yeah, to balance up on the other side. Now we've got the problem of having hydrogen. Okay, we'll put hydrogen ions in. Okay, so we've got 4 lots of 2 hydrogen there, so we need 8 H plus, -1, 8 plus, -7 on this side. Okay, so sorry, +7 on this side. Okay, so it's +7 on the left hand side, +7. Okay, we've got +2 on the right hand side, so let's bring this down by adding electrons. +7 -5 makes +2, +2 now on this side, +2 on this side. Okay, so it's balanced. Okay, a change. Right, it goes purple, from purple to very pale pink or even colours. Okay, so oxidation, we could use the potassium manganate to oxidize iron from iron 2 plus to iron 3 plus. We can balance this equation as well. Very simply, we just need to add an electron. Okay, so now there's a question on that, question on page 10 in the booklet. Okay, so please, I would like to suggest that you stop the video and carry on when ready. Stop the video, carry on when ready. Okay, move that out of the way and let's carry on. So hopefully you've done that question. So balancing out electrons. Okay, so for this one, we had the iron there, we had that, and it's just the same process before, or it's the same as before. We need to get the electrons balanced. We need to add 5 lots of the top equation to give us the right number of electrons. So add the 2 equations together, okay, cancel the electrons, we end up with our final equation. H plus, remember we said that comes from sulfuric acid, okay, which gives us our H plus ions. Okay, so now you might have asked this question last time, why not use HCl? Okay, well, the problem is that chloride can be oxidized. Yeah, it can be oxidized to chlorine by using the oxidizing agent O4. So sulfate does not do that. Okay, so that's why we don't use HCl. Okay, so now an example calculation. So this is where we're coming on to the titration aspect of it. So we need to be able to remember our equation, which is the moles equals concentration times volume. Or, because we've got it in centimeters cubed, moles equals concentration times volume over 1,000. And you can work either way. I mean, for me personally, I would go that 25 centimeters cubed is actually 0.025 dm cubed. Yeah, and 23 centimeters cubed up here is 0.023 decimeters cubed. It's quite an easy calculation to do in your head, just divided by 1,000. Okay, so we've got 25 centimeters cubed of a solution of iron 2. So we don't know what the concentration of iron 2 is, but we do know that it needed 23 centimeters cubed of potassium manganate to react with it, and we know the concentration of the manganate. Okay, so let's have a look at how we'd go about that. So first off, like most calculation questions, we need to work out moles. So we need to work out the moles of manganate. So we've got volume of 23, concentration of 0.02, so moles equals concentration times volume over 1,000, or you can do it in your head, and that comes out as equal to 4.6 times 10 to the minus 4 moles. Now, deduce the number of moles of iron in there. Now, the ratio from our previous equation was that there's 1 mole of this to 5 moles of this. Let's just recap that. So here we have this, yeah, so we've got 1 mole of this to 5 moles of that. Okay, so the ratio is 1 to 5. Okay, so therefore we need to multiply this value here by 5 to get the number of moles of iron. Okay, so 4.6 times 10 to the minus 4 moles of manganate will react with this amount of iron 2 plus. Okay. calculate concentration of iron 2 plus. So we now just need to do concentration is number of moles times the volume, number of moles divided by volume. So because we're doing it as 1,000, we're doing it as centimeters cubed, is n times 1,000 divided by the volume. So n times 1,000, well, we had that, okay, divided by 25 gives us that many moles of iron 2 plus. Okay, so we have now worked out, okay, we've worked out the concentration of this solution. Okay, so now it's your turn. So you would need to construct an equation for the reaction of it with ethanoate iron. So here is the ethanoate iron. We've given you the half equation. Okay, so this is a balanced half equation for the ethanoate iron. So basically it's, it might be worth just seeing that molecule, what that looks like. Okay, it's quite a simple molecule. So C, it's a dioic acid. Okay, and so there's, now as the acid, it would have the hydrogen on there, but as the ethanoate, the hydrogens come off, so those are both negative. Okay, so you can have a go at doing that. So what I would suggest you do is, guess what? That's right, stop the video, carry on when you're ready. Okay, so let's just get rid of that. So that's my pen. Okay, so if you have done it, you should have worked out that this is the equation of how they balance. Okay, there's the equation there. Okay, you can stop the video if you need to. Right, okay, so now we have an equation to do with titration using this equation. 25 centimeters cubed of sodium ethanoate solution of concentration this is warmed and titrated against a solution of potassium manganate 7. If 17.2 centimeters cubed of potassium manganate is required, what is the manganate's concentration? So working the other way. So let's go through the answer. The number of moles of ethanoate in 25 centimeters of solution concentrated is 0.2 times 25 over 1,000 equals 0.005 moles. Okay. Okay. Ratio of ethanoate to manganate is 2 to 5. Okay, so the number of moles of manganate, okay, ethanoate to manganate, it's 2 manganate to 5 ethanoate. So we have to do the moles of ethanoate times 2 divided by 5. Gives us that amount. So now we need to work out the concentration. Okay, well, we've got 17.2 centimeters cubed. Okay, the concentration equals moles divided by volume. Well, the volume is times 1,000 at that because it's in centimeters cubed. Okay, and that gives you that concentration. Okay, so now potentially, okay, in the lab you will see this demonstration. Okay, and it's hydrogen peroxide makes oxygen gas, so there's a big expansion in gas. We'll try and work out the oxidation. Oxygen is both oxidized and reduced during this reaction, yeah, because we've got it as -1 here because it's a peroxide. Remember, that's the odd thing with oxygen, is that when it's in a peroxide like this, its oxidation number is -1. So it's -1 here, it's -2 in water, and it's 0 in there. So it's both been oxidized and reduced. Okay, so disproportionation. Recap of that. Okay. So we catalyze the reaction with potassium iodide. Okay, and we could write. Can we write a mechanism? Okay, so this is a bit of a recap of various bits and pieces done previously. So the rate is K peroxide times iodide. So it's first order with respect to both peroxide and iodine. Okay, so it means that peroxide and iodide must both be in the initial or the rate determining step. So something we could sort of suggest is that, okay, we can get that, we could get an iodate intermediate. That iodate intermediate could react with another peroxide. So remember, it's 2 there, but because it's a first order with respect to peroxide, only one of them is likely to react in the rate determining step. The iodide must be included because it's the rate determining step and it's in the rate equation. And again, it's only one iodide there. Okay, so because it's the first order. with respect to iodide. The overall reaction is, yes, you guessed it, second order. Okay, so if I remove one oxygen, I'm getting close to my products. And one of my products is water, so I've got one molecule of water, and I've got an intermediate here. Well, I can just use that intermediate. I'll use that intermediate to pull another oxygen off and make H2O, okay, again, plus oxygen plus iodide. Okay, and so yeah, we've got our overall reaction, and of course the iodide has acted as a catalyst because we used it at the start and then it's been reformed. Pretty exothermic, so we might get the foam steaming. So okay, there are some other bits and pieces in the reaction just to give it the nice foam. So brown discoloration, okay, because you know, it's iodine. Yes, you might have some iodine in there. Some of the iodide iron may be oxidized in a side reaction. So there is a possible side reaction, but that gives it slightly yellow and perhaps browny color. Okay, the second demo you probably will see is the Thermit reaction. You hopefully may have, well, you may have seen it before, but it's aluminium reacting with iron 3 oxide, and we get molten iron. Competition reaction. Aluminium is more reactive than iron. Okay, equation of the reaction uses oxidation to show what's been oxidized and what's been reduced. Can you write the half equation? So whilst you go and do that, you should stop the video and carry on when ready. Okay, so here are our half equations, or here's the main equation, and then we need to get the half equations. So we've got iron 3 oxide reacting with aluminium, making aluminium oxide plus iron. So aluminium's gone from 0 to +3, so we need to have that. Aluminium becomes Al3 plus 3 electrons. Iron has gone from +3 to 0, so it's been reduced. So Fe3 plus 3 electrons makes Fe. That looks quite good because we've got the same number of electrons in both half equations. And so that's how you can put this equation together. And that basically is it for 23.2. Okay, here's our task menu, so you should go and have a go at those questions in your booklet and just obviously practice.